go. Let's do this.
You recording?
Yeah.
Hi!
Hello.
And an introduction to the previous presentation.
Now, let's quickly, has everyone got this photocopy still in their books?
Yeah.
Alright, we just want to review what we thought about last time of these slope fields and how to interpret them. I need you to jump on the Google site for that section and look at some more tutorial videos on that to get a more detailed understanding. Okay? What you have to look for are some key things to interpret from this graph. Axes intercepts, X and Y intercepts. So you've got to think about what's happening to the gradient at the intercepts as well as quadrants. So that's one thing. And the other thing is the behavior of the tangents, these little tangents, in each quadrant. Okay? So you've got to examine the slopes, direction of slopes. In each quadrant. So, let's think about, first off, let's look at some x-axis intercepts. Okay, so over here, when x is positive, let's note down a property. When x is positive, okay, and y is 0, that is identifying this part, your x-axis, positive x-axis. Does that make sense? Then what is dy dx looking like? They're all coming down this way. Can you see? That is negative, less than 0. Do those little... Okay, so that's one property by examining the axes. Okay, what about on the other side? Okay, on this other side, we've got this part here past a particular point. You've got a mix of both. You've got your little tangents coming down this way, it looks like a positive tangent, but on this side of the axis, past this interesting point here, and we'll look at that very shortly, we've got the tangent swapping. They're negative. Okay? Alright? So, we think about now, at this particular point here, what do we have? That point, what do you think that looks like? That's a 1, 2. That there is at a x equals a minus 2. Okay? So, where we have x equals less than that number, we've got one direction, and x equals more than that number, you've got another direction. Okay, so x is greater than a negative 2, that point, and we can, you can look at your answers and think, well, that point there is an interesting point. That's referring to something that's happening at a particular x and y number. You can look at the answers, and the only x and y numbers there of interest are 2, or minus 2 for x and positive 2 for y. Yeah? So when x is greater than that, okay, when y is 0, then we end up with a dy dx. That means, look on your axes to the right of this point, minus 2, and you can see the little tangents are negative. Yeah? But when x is less than minus 2, that's all numbers to the left, this side. When y is 0, then our dy dx now tend to go up this way. Alright? Which means that they're positive. So where identifying some behavior, okay, of our gradient by examining what the little tangents are looking like for particular conditions on x and y. Does that make sense? So you can now examine some of these rules and see if these rules themselves matches this behavior. Okay? And then we can also do the same for the y-axis if we're stuck. So let's choose, start with A. Alright, so all these we've looked at this behavior on the x-axis intercept when y is 0. So you look here, you make y equals 0. Okay? That means you're going to be dividing by a negative 2. Alright, so it makes this fraction negative. Yes? This fraction is negative. Then we make it negative again. So it's positive. Okay? So positive for when x plus 2. Okay? Now, for when that is x is greater than 0, okay, when x is greater than 0, what should the direction of dy dx be? We said it's negative, but this here will become, when x is greater than 0, this bit becomes positive. Isn't that right? So does that match? No. What about, let's have a look at B. So, again, we're looking at the x-axis intercept. We make y equals 0, put that 0 there. That makes this negative fraction because we're dividing by negative 2. So it makes it a negative fraction. Then we might say, all right, let's check this one. When x is positive, okay, when x is positive, then this fraction here becomes negative overall. The numerator is positive, but the denominator is negative because we've divided by 0 minus 2, negative. Okay, so that satisfies this one, good. Don't jump the gun straight away. Make sure you can tick the box with some other patterns, yeah? So what about if we have a look at this condition number 3 over here? So again, x is 0, divide by negative 2, which makes this fraction negative, okay? Now, when x is less than negative 2, if I put a number less than negative 2 there, then I get positive overall, isn't that right? The numerator is negative, the denominator is negative, which makes it positive, and that's consistent with what we saw on the axes. Okay? Tick. So we've ticked that one, we've ticked that one. If you can tick off 2, it's highly likely that's the correct answer. Okay? Sometimes you need to just be careful, check one more time. Alright? So that's why it's good to do at least 1, 2, or 3. Even if you do it with, now, what about a behavior on the y-axis? So on the y-axis, x goes to 0. Let's say when y is less than, and the important number that we can see where things change is 2. When y is less than 2, there's y equals 2 there, then look at the slant of our tangents, negative. Does B follow that condition? Let's check. All right. Let's make x equals 0. So put a 0 in your numerator. So the numerator overall is positive. Yeah. Divide by. Now, we're making y equals less than 2. So a number less than 2 subtract 2. What happens to the denominator? Negative. Yeah. Positive divide negative is negative overall. Ah, that's consistent, isn't it? So we're pretty certain there. Okay? So if you go down the list and one fails one of these axes conditions that we've identified, then you know, no good, move on to the next. Okay? Until you're confident with a minimum of 2, it's probably best to be safe, try 3, okay? Try and pick out 3 conditions by looking at the axes. If you can tick the box for 3 of them, then put a circle around it. Does that make sense? Beautiful. So that's strategies in answering these types of questions. You can examine the intercepts, x-axis and y-axis intercepts, and set up conditions like so. Or you can examine the quadrants themselves for particular types of things, okay? Very good. So, we're going to be moving forward because we need to start some work on kinematics. To begin with, okay, we're going to look at some kinematics involving constant acceleration and look at applying Newton's second law and see what that means. So, physics students, let's get you guys to contribute. Newton's second law. Sum of all forces equals the mass of an object multiplied by its acceleration.
Are we going to be looking at it vectorially yet?
Yes, not straight away, but very soon we'll be looking at it vectorially. That's correct. So, all motion is governed by forces. Okay, applied forces on an object. Forces can occur in all different directions on an object. Okay, pushing and pulling in all different directions. So you look at the overall, what's the overall push and pull on an object, and that overall push and pull will determine the direction it's going to start moving.
That's just the net force?
That's called the net force, that's correct.
Are we going to be learning about complex areas of kinematics? So for graphical gravitation, you'll have the x, y, and z?
3 dimensions? No, not 3 dimensions. Only rectilinear motion, 1 dimension. Okay? And then when we look at vectorially, we will look at vector functions in terms of then 3 dimensions.
Is universal motion?
No, 2 dimensions. I and J mostly. A little bit of K. Okay, so it was all based on these guys' work. Okay, from 1660 of Newton up to Lagrange in the 19th century. They were all pretty hip. So, we'll give it to him instead. Okay. So we say a kilogram of mass accelerating at 1 meters per second will give you 1 Newton of force. Okay? The type of forces we're going to have is a weight force. What's a weight force?
Pulling down.
Pulling down force due to? Gravity. Force due to gravity. Force due to gravity. Direction is? Vertically downwards.
Not to the left.
A little bit to the left.
Yeah, I actually said gravity goes to the side.
Okay. Weight force is given by, we sometimes refer to it as W. Mass times the acceleration due to gravity. Okay? Now, our acceleration due to gravity we're going to be using is here on Earth. Every object accelerates towards the ground at 9.8 meters per second squared. Right. Okay. Now, a normal reaction force is a supporting force. Okay, it's a supporting force that every object that's in contact with a surface, that surface supports the object or pushes back on the object perpendicular to its plane. Okay? So it's a supporting force on an object, and it always acts perpendicular to the plane of the surface. Okay, so if you have a little surface, say, like that, and you've got an object sitting on it, then of course the surface supports this object or pushes back on the object at 90 degrees to the surface, okay? And we call that the normal reaction force. Same with curves, okay? If an object is sitting on a curved surface, the normal reaction force will be perpendicular to the tangent of that curve. Alright? And we call that, what line do we call perpendicular to a tangent? A normal. Yeah, the normal line. Because it's like that of a normal force. Does that make sense? Okay, so some other forces we're going to encounter as well. We've got a driving force, okay? This is an applied force. It could be constant or non-constant. So it could be a force, a driving force could be, say, maybe a function of time, for instance, or it could be a force that is a function of velocity or something else, but it exerts, it pushes an object forward. Force due to air resistance.
Would a driving force be as a result of like an engine or something?
Could be an engine, absolutely. Could be the result of an engine.
Or a rocket?
Or a rocket. Yeah. Result of an engine. Or rocket. Or it could be a simple push. A physical push. Okay? I could push an object forward and that would be a driving force. That's pushing it forward. Very good. Well done. Komal, you just applied a driving force to area. And Karen. Very good. Okay. Due to air resistance. So, an object that is falling downwards, that is accelerating, it experiences an air resistance that is opposing the direction of motion. Okay, so air resistance depends on velocity. Okay? It's velocity dependent, so it's a function of velocity. Okay? So in this case, you might have some constant multiplied by V for linear air resistance, or it could be you can have quadratic air resistance. Okay? Now it doesn't have to be air resistance as such. Air is what we describe in our everyday surrounding, in our everyday experience. The medium for which we exist in is air. But it doesn't have to be air, it could be any medium. What's another medium we have here on Earth? Water. Yeah? Another medium we have here on Earth is water. So we can have not air resistance, but we could have water resistance or any fluid resistance. Hello.
Hello. Would you like a 2-hour or a 2.5-hour practice exam for Year 12 physics? Because the actual exam is 2.5, isn't it?
Yes, Year 12 physics.
Yes.
Well, I think
Is it physics?
it will need to be 2 hours, I think. Yeah, better check with Carl on that one.
Carl was told physics.
Yeah,
Oh,
sorry.
What did I just walk into?
Specialist.
Sorry.
That's all right.
To me, they sound the same.
Yes, but I'd say 2 hours. 2 hours would suit.
Do you do Ken or again Carl?
Carl.
Sorry, mate.
That's all right.
That was Andrew, ladies and gentlemen, listening at home.
Yeah, thank you. Now, what you'll find, resistance in the air medium, it behaves such that the force depends on a velocity squared. Resistance in, say, a water medium would actually be a linear function of velocity. Okay? It's got to do with the viscosity of the medium.
Oh, so I said the drag.
Yes, the drag constant is built into K, but its behavior when an object moves through water, its resistance force is more directly proportional to velocity in a linear function. Whereas when it's moving through air, it's proportional to a velocity squared, parabolic.
Okay.
Okay? Then friction, sliding, you've got two types of friction. You've got what's called static friction. This is a friction that makes objects stand still on a surface. Okay, and we have kinetic. So kinetic friction is friction opposing a moving object. Slows down a moving object. Okay? So friction always follows the same kind of formula. So it is force of friction is equal to the coefficient of friction, which is some proportionality constant, multiplied by the normal reaction force, or just the size only, the magnitude of the normal reaction force. So the reason why is because if you rub your hands together lightly, don't put too much pressure together, rub your hands together, it's nice and smooth. But if you push your hands really hard together and then try to rub, it's a lot more resistance, isn't there? Okay? It's because the harder you press your hands together, you're increasing the contact force between your hands, which increases the normal reaction force that one hand applies on the other. Okay? And so that increases the resistance to move. That increases the friction between your hands. Does that make sense? So you've got two types of friction. You've got a static friction coefficient, and you've got a different kinetic friction coefficient. And we're going to look at that behavior of friction force a little bit later on. Okay, so that's just an outline of some of the forces we're going to be working with. Yep. Mu S for static friction coefficient, which is different to mu K, which is a kinetic friction coefficient. F equals mu times the normal force.
Say with the end.
Hmm?
Say with the end.
Moo.
You sound so defeated when you say it.
Moo. Now, so the first kind of situation we're going to examine is what happens when we've got an object in a simple situation. So let's look at a falling object. Okay? Any falling object? When we're looking at falling objects or moving objects or any object that's experiencing a force, and we try to write it as a diagram, we don't want to get, artistic and try and draw a full diagram of all the parts and moving. We simplify a complex diagram into a dot, and then we can draw forces with directed arrows. So
Freebody diagram?
this is called a free body diagram. It's a diagram that is free of its body. Okay, we represent as a dot. Okay, so we just draw a dot to show a force. Let's include one of the forces. What's W stand for?
Weight force.
Weight force. Very good. Weight force is the mass of the body times the acceleration due to gravity. Okay? Now, this here is a constant force all the way down because G is a constant that doesn't change. 9.8 meters per second for every second. Okay? And mass is measured in kilograms. Okay? So this is a constant force, and let's use Newton's law. What we have here, the sum of all the forces must equal to mass times acceleration. Okay? There's only one force acting on this body, and that is the mass times the gravity, which is the weight force. Yes?
Would you have a person
Normally we would. This time, we're under this this is the first simple case we're going to look at. In reality, we would have, yes, some air resistance, okay, that opposes its motion. But in a simple case, we'd like to start off and assume no air resistance. So this is what you get when you assume no air resistance. This is what you get when you've got motion out in a vacuum, like space. Okay? Free body diagram. Okay, so in this case, the acceleration we have is just equal to the acceleration due to gravity directed towards the ground. And this here is what you call a differential equation, believe it or not. Okay, that is a differential equation. Now, what do we know about A, acceleration? Yes. Acceleration is the rate of change. We've got a change in velocity for every amount of time, change in time. Okay? Now, this is a big change in velocity and a big change in time. That's our average acceleration, or average rate of change of acceleration. So, a average. But what we're interested in knowing is what's the instantaneous rate of change of acceleration. And our instantaneous rate of change is the derivative, dv dt. Okay, so let's use our differential equation. dv dt is equal to g. Alright, that's a constant number g. So dv is equal to g times dt, multiplied by dt to the other side, and then I'm going to integrate both sides, and I get v is equal to g times t plus c, our integration constant. Okay?
So would you let V equals U?
Yes, that's correct. So for our, what happens in any falling body, initially we might hold it and drop that object from rest. Okay, from hold it still, it's stationary, its beginning velocity or initial velocity is 0, and we drop it. But we could also throw it down. Okay, so it's got a non-zero initial velocity. So we need to know a little bit about what happens at the start, its initial velocity. Okay? So the initial velocity we're going to call a u as opposed to a v. So from that, when t is equal to 0, we've got at the start of the motion v is equal to a u, and so we use that initial condition in our solution so far, and we get the integration constant will equal to u. And put that back in, we achieve this. Okay? So this is the solution. This is the solution of velocity as a function of time. Okay? Velocity as a function of time. The initial velocity plus acceleration multiplied by time. So we can extend that now. We'd like to know what is the position of the object at any point in time. So what is velocity defined as? dx dt. Yes, that's right. It's a rate of change of position or displacement with respect to time. dx dt. Okay, so x is what we call position. Okay, and the position is, some coordinate in space, in xy plane. Yes, Josh?
Is gravity constant?
Yes.
Can gravity be right at the front?
Yes, it can be. You can also leave it in. That's okay. Oh, G. V equals AT or GT. That's okay. Now, this dx here, that dx where it's your instantaneous change in position. So what we're interested in is knowing from a position, we're going to define a big change in a position. A change in position we call what quantity? Displacement. Okay? So if I take 3 steps, the 3 meters to the left, my displacement is 3 meters to the left from my beginning position. Okay? That change we're looking for. So working with this, I can set up a second differential equation. dx dt, which is my velocity, is equal to a u plus gravity times time. Okay? And now I separate and I integrate. What's the integral of constant number u? Ut. What's the integral of a t term with respect to t. Half t squared, that's right. So I get a half acceleration due to gravity, t squared, plus c. Don't forget the plus c. Yeah? Alright. So then from there, I want t is equal to 0, and x is going to equal to what it was your initial position. Okay? Not always 0, it could be anywhere. You could be initially 10 meters off the ground. Yeah? So we're going to call that x0, which is your initial position. Does that make sense? So your initial position now is your x0. Let's put that back into, let's do this substitution. T equals 0 in all your terms. And I obtain the c is equal to the initial position. Okay? Okay, and we end up with this by making use of our integration constant c, okay? Then if I put c is equal to the initial position there and subtract that over with x, here is my change in my final position to my initial position, which we call delta x, which is your displacement, okay? So your displacement is given by ut plus half a squared, t squared, which is your acceleration. In this case, we're accelerating downwards. Sometimes what we're going to do is call this a different pronumeral. We might call it s. Okay, is the common pronumeral that represents a change in position. That's your displacement. X is a position, whereas s is a displacement. Does that make sense? Okay, now one more important thing we need to look at is what happens if we have no measurement of time in motion. Okay? So, what we have here now, let's come back to our acceleration. We've got our okay. Here we have let's come all the way back to our first equation. Acceleration is equal to g. Okay. Now, acceleration was the rate of change of velocity with respect to time. Was some constant. Now, we're going to do a little trick to remove our t. Okay. So, we're going to use chain rule. Okay, so let's express this rate. Recognize this here as a rate of change of velocity with respect to time. And we're going to now relate that to other rates of change, like we've been doing in concentration formulas and things like that. Okay, so a related rate of change here is, using a chain rule, is introducing the x as a position. Okay? But then we have to multiply by dx dt, applying the chain rule for it to be equivalent, for it to balance. So, what do we know about dx dt? What is that? It's the change in position with respect to time. What do we call that? Velocity. The rate of change of a position with respect to time is a velocity. Okay? And so our dv dt, our dv dt really is now a velocity multiplied by dv dx. The change in velocity with respect to position. Okay? So we're going to use this interesting form of acceleration. Acceleration is your dv dt. Okay? Acceleration is also a velocity multiplied by the rate of change of velocity with respect to position. So v dv dx, coming back to our first original differential equation for constant acceleration g. Okay? So now what we have here is, let's separate our variables. V dv on this side is equal to a g dx on that side. And now we're going to integrate both sides. Yes? What's the integral of v with respect to v? Half v squared. Okay? And now let's integrate a constant number with respect to x. And you get gx plus c. Okay? Now let's look at an initial condition. So initially is at the start of motion, t equals 0. Alright, now we have no variable of time in this formula, but you need to think about at the start of my journey, when I start timing, I'm in my initial position and I have some initial velocity. Okay, everything is, this, what are my quantities at the start? So my x is a initial position, x naught, okay, and my velocity is some initial value u, initial velocity. Does that make sense? All right. So let's now apply that to this rule. We're going to get a half v squared, which is no longer v, it's called u in the initial position. A half u squared is equal to g times x naught, initial position, plus c. Okay? So c must equal to a half u squared minus gx naught. Yeah? Alright, let's substitute that back into our dE. Half v squared is equal to gx, okay, and we've got plus a half u squared minus gx naught half v squared is equal to, now I've still got my half u squared, but now if you have a look, I've got this two terms with a constant factor of gravity, so I'm going to take that out, gravity as a common factor, and what is left is a x minus x naught. Okay? And I'm going to transpose for, say, the final velocity, knowing something, what happens at the end. Alright? So my v squared, to do that I'm just going to multiply each term by 2. So I get 2 times the right-hand side. 2 times this first term just goes to a u squared. Okay? Plus 2 times this term will be a 2 times the acceleration due to gravity times this subtraction of position. How do we interpret this? S, which we call the displacement. Okay? Now that's very important because in these rules you might be familiar with some of these rules, but you can't interpret the x as some distance traveled or some position. It is a displacement. Okay? They are all vectors. So the vectors are v, u, s, okay, and acceleration a. They can be both positive and negative. They all belong, they're all elements of the real number set, okay, which means that they can be positive, they could be negative, okay. So it's important to consider that more carefully. So you've got a set of those rules here, and we're going to apply them in any different type of problem. So let's try this. Child slides from rest down a slide 4 meters long. The child undergoes constant acceleration, okay? Doesn't always have to be g being 9.8, it could be any type of constant acceleration value. This one here? Yeah. So I want you to think about what this is. This is a u plus a v, divide by 2. If you've got two velocity numbers, you add them together and you divide by 2, what are you finding? The average. Yeah? Two numbers, add them together, divide by 2. That's the average. So this here is an average velocity, okay, times by the time of travel, gives you the total displacement. Okay? We don't need to go about proving that by calculus. Reaches the end of the slide traveling at 2 meters per second. Find the time taken to go down the slide. Okay, what do we know about what things can we what quantities can we determine? What do we know about u? Initial velocity. U is 0. So we look for keywords like at rest or from rest, which means initial velocity is 0. Child undergoes constant acceleration, which means big tick for these rules. Okay? And reaches the end of the slide traveling 2 meters per second. At the end, we've got a v equals 2. Yes, and we've got a change in position from the start to the end. That change in position there is the s, the displacement. Okay? And our job is to work out the time taken. So what rule has velocities, displacement, and a time? Last one? Yes. Last one is a good one. Okay? So last one is one of those rules that help you to make use of those quantities we've determined there. Okay? So you identify what's the most appropriate rule from the values you've got in the question. And we transpose, we then can go about transposing our rule for the quantity we're after. We substitute the values in and we get a result. Okay? Happy with that? The acceleration when the child experiences what? Oh, the acceleration which the child experiences. Sorry, I got to read English. So now we know time, we know final initial velocity, we have to work out acceleration. First one. V equals u plus at. Alright? And we have to transpose the rule for the variable we're after, a, sub in our values, and you get your quantity. Now, I want you to think about how we represent these physical quantities. This is a time written in seconds. This is an acceleration. How do we write the units for acceleration? That's correct. Meters per second squared. So we got to make sure we're consistent with the correct units of measure for our quantities.
I guess physics are that.
Okay?
It's like, you know, whole human figure.
Okay.
So you went from single syllable to the back.
So,
Sorry, John.
what I want you to do now is just to explore, for part of your homework, a set of exercises on these to practice identifying those quantities, choosing which rule you have to work with, okay, and then substitute and transpose your rules for what you need, okay? We're going to, I want you to have a go for homework, those exercises. Then our next class, we're going to look at a challenging one. One that you wouldn't get in physics class, normal physics class, specialist maths level exercise. But to start off with, just try a few versions of these types of problems, okay?
Oh my god, that's what we're writing is. Oh my god. I tried to write it.
So, we're looking at, in your Google site, this part here, please. What I'll do, I'll update the site to have the Cambridge exercise. So I've got, these ones here. For some work, this is from formula, and then this is on graphs, motion graphs. Okay? And we'll see how the motion graphs is built into this next class with our exercise, okay? But it's this set of exercises that I'd like us to start working on, please.
So are you going to upload yesterday's notes?
Yes, I'll put yesterday's notes up, and